These are practice exercises from page 83 and 84 of the textbook. We're going to practice writing balanced equations and predicting products. In the first one, we've got solid mercury 2 sulfide decomposing into its component elements. So if we look at the way this is worded, a decomposition reaction, so I know it's a decomposition reaction, happens when I start with something that looks like AB and it turns into separate A plus B. So we start with something that's together and we end up with two separate pieces. In this case, they're telling us that we're starting with solid mercury 2 sulfide. So we want to think about what the charges are there. Mercury has the symbol Hg, and since it's a transition metal, that's why they give us that Roman numeral. The Roman numeral tells us the charge, so I know that this mercury has a charge of 2 positive, and sulfide comes from sulfur, and if I look at where sulfur is in the periodic table, I know that sulfur as an anion will have a 2 negative charge. So if I look, these two charges are going to fit together, a +2 and a -2, so the formula for mercury 2 sulfide is just Hg. And they specifically told me that it's a solid, so that goes in parentheses after. It's decomposing, so I know it's turning into products, so I use my reaction arrow, and it says its component elements. So mercury sulfide is made up of mercury, which is a liquid at room temperature, and sulfur, which is a solid at room temperature. So if I go ahead and look, this is balanced. There's one mercury atom on the product side, one mercury atom on the reactant side. Same thing with the sulfur, one on the product side, one on the reactant side. So this equation is complete, it's balanced, and I have all of my state symbols written in. Let's do the next one. In this case, I've got aluminum metal combining with oxygen in the air. So this is a combination reaction. This is the opposite of decomposition. Now I will start with two separate pieces, A and B, and turn them into one new compound, AB. So again, let's write out what we know. We're going to start with aluminum metal, which has the symbol Al. Aluminum metal is a solid. It's combining with oxygen. Oxygen is one of the 7 diatomic molecules. So it's oxygen, nitrogen, hydrogen, chlorine, fluorine, bromine, and iodine. Whenever you see those, it's always 2. So oxygen's always O2, unless it's in a compound, but oxygen by itself is always O2, so it's oxygen gas. And the question is, what is it combining to make? So again, we want to think about the charges. Aluminum, based on where it is in the periodic table, has a 3 positive charge. Oxygen has a 2 negative charge. So when I write that formula, it's going to be Al2O3, and that is going to be a solid at room temperature. So make sure when you're writing these reactions, you are thinking about how the individual atoms fit together to make compounds. Okay, now if we go ahead and look at this to balance it, you should see that I've got 2 aluminum atoms on my product side, but I only have 1 on the reactant side. That means that I'm going to need more aluminum atoms. I also want to check the oxygens before I get started. I have 3 oxygen atoms in the product side, and I know that they come as groups of 2 on the reactant side. So there's no way to turn this group of 2 oxygen atoms into 3, because nothing, no whole number, times 2 is going to give me 3. So what I'm actually going to need to do is I'm going to need to double the product, which gives me a total of 6 oxygen atoms, because I take the 2 from the coefficient multiplied by the 3 on the subscript, so I've got 6 oxygen atoms. And if I've got 6 oxygen atoms on the product side, I also need 6 on the reactant side, and the only way to do that is to put a 3 in front of the oxygen. So now my oxygen atoms are balanced. I've got 6 on each side, so I can turn my attention to the aluminum. Again, the coefficient of 2 gets multiplied, so I've got 2 groups of 2 aluminum atoms. That's a total of 4 aluminum atoms on the product side, which means I also need 4 aluminum atoms on the reactant side. So this equation is 4 aluminum react with 3 oxygen molecules to make 2 aluminum oxides. Alright, last one is a little bit different. Now we are looking at a reaction with burning, and that is a keyword for a combustion reaction. In a combustion reaction, I always have a hydrocarbon reacting with oxygen, And in our case, we're always going to assume complete combustion, so we're always going to assume that we get carbon dioxide and water. Combustion is not always complete, but for the purposes of this class, we're going to assume complete combustion. Now, a hydrocarbon is typically composed of carbon and hydrogen. It can also have oxygen. So we see that our hydrocarbon is ethanol, and they're giving us the formula for ethanol, C2H5OH, and they're telling us that it's a liquid. We know it's going to combine with oxygen from the air. Again, oxygen's diatomic, and it's always a gas. And we know that it has to produce carbon dioxide, which is a gas, and water, which after a combustion reaction will be a gas because of the heat. So combustion reactions are a little bit easier because you know exactly what's going to happen in the products. Your products have to be carbon dioxide and water, and you always know that oxygen is going to be reactant. So now we just need to go through and balance this. Something to be very careful of, something to watch out for. There are 5 hydrogen atoms here, and there's a 6th one hiding here. So since there are 6 hydrogen atoms on the reactant side, there need to be 6 hydrogen atoms on the product side. Since the hydrogen atoms on the product side come in groups of 2, I only need 3 water molecules in order to have these 6 hydrogen atoms. The next one I'm going to take a look at is the carbon. So I see 2 carbon atoms here, but only 1 carbon atom here, which means I'm going to need to double the carbon dioxide. If I have 2 carbon dioxide molecules, that will give me the 2 carbon atoms. You'll notice that I started with the carbon and hydrogen, and I left the oxygen alone. The reason for that is, it's easier for me to follow what's happening with the carbon and the hydrogen. The carbon only occurs here, and the hydrogen only occurs here and here. The oxygen's a little bit more confusing to deal with because every single compound in this reaction contains an oxygen atom. So I'm going to leave oxygen for the end just because it's going to be more difficult to balance. So let's count up the total number of oxygen atoms we have. On the reactant side, we've got 1 inside our hydrocarbon, and we've got 2 on the oxygen for a total of 3. And if I go on the product side, 2 times 2 means 4 from here, and 3 times 1 means 3 here. So I've got a total of 7 oxygen atoms on the product side. I need to figure out how to get 7 on the reactant side. I know that I'm always going to have 1 hiding in the hydrocarbon, so I really only need to get 6 oxygen atoms from the O2. Because in this case, 3 times 2 is 6, plus 1 is 7, and that matches because I had 4 here plus another 3. So now I have 7 oxygen atoms on each side, so this combustion reaction is completely balanced. Again, make sure that when you write these, you're making sure you have the right number of atoms on both sides, make sure you're doing your formulas correctly, and make sure you have the states in parentheses after each of your substances.